we have studied the standard normal random variable, and we have said that both the normal random variables and the standard normal random variable, their cumulative distribution function do not have a closed form formulation. So therefore, we have shown some propositions where we say that a normal random variable, when it is linearly transformed to another random variable, that other random variable is also a normal random variable as well. So normal random variable is not changing its probabilistic properties up to linear transformation. And the only thing that changes in this linear transformation is what? The parameters of the normal random variable. So this new random variable is also normal, but with different parameters, which are a mu plus b and absolute value of a sigma, where a is the multiplier and b is the intercept term in this linear transformation. And secondly, we have said that now it is also possible to transform the normal random variable to a standard normal random variable if you subtract its own location parameter from a normal random variable and divide this difference to its own scale parameter, then that normal random variable will be converted into a standard normal random variable. And that means we can calculate probabilities related to normal random variables by linearly transforming them into standard normal random variables, which means this operation is called standardization, which means we are subtracting the location parameter from the both sides of the inequality and divide the difference to the scale parameter, and that is going to give you the probability that you are looking for from the standard normal distribution. So the probability of a normal random variable to be less than or equal to an arbitrary x value is equal to the probability of a standard normal random variable to be less than or equal to x minus mu over sigma. I am very sorry, my friends. I have spoken in the simulation course in the last 3 hours, and now I'm going to speak for you in the next 3 hours as well. So I do not want to have any complications, so I just need to clear my throat in the beginning. Sorry. Okay. So by the cumulative distribution function of the standard normal random variable, we can identify probabilities related to non-standard normal random variables. So this means we need to, even we cannot compute these cumulative probabilities for standard normal random variable, we can approximate them numerically by using numerical integration methods, and we can store these approximate values over a table, which is called the CDF table for the standard normal random variable, which you are going to use in your exams as well. And we can use this table in many perspectives to calculate probabilities related to standard normal random variables. Now, yesterday we have practiced those already, so I'm not going to repeat them. So I will move forward to these pages and I will start from question 11. Okay, so this was the point where we have left in yesterday's class. Okay, so it says, consider Z as a standard normal random variable. Consider Z as a standard normal random variable and identify the x value for which the probability of Z being less than or equal to x is 0.60. Okay, now this time, unlikely to the previous question that we have solved yesterday, this time we are not being asked the probability of Z being less than or equal to or greater than or equal to something. This time we are given the answer, the probability, and the question is asking for which value of x the cumulative probability is going to be equal to 0.60. Okay, so if we find the answer for that, we need to check the normal table from a inverse perspective. Okay, inverse perspective. So I am going to open this PDF file. My friends, I don't know if you can see it. Can you see the PDF file for normal table, normal distribution table? Can you see the table? No, okay. So I am just going to share. Okay, I'm going to share my whole desktop with you. Okay. Now I think you are supposed to see the table. Okay. So remember now, what was my question? The probability of Z being less than or equal to X must be equal to 0.60. So I need to identify this critical X value for which this probability is exactly equal to 0.60. Now let's check. Let's check. This time I am going to look at the X values, but I need to find the probability as 0.6. Okay. So this time probability is going to be equal to 0.6, the cumulative probability, which is the area on the left-hand side of X must be equal to 0.6, and I need to find the X value. So where are these values? Where is 0.6? Check this out. Where is 0.6? It is somewhere between these two values, right? 0.5987 and 0.6026. Now they are between these two values. So this means the critical X value, the threshold X value that we are looking for should be somewhere between 0.25 and 0.26. Okay, 0.25 and 0.26. So we can see that in the presentation file as well. So I am looking for the probability to be equal to 0.60, but I cannot see that probability exactly here. So X value should be somewhere between 0.25 and 0.26. So what I observe is this. For X value, which is 0.25, the cumulative probability is 0.5987. And for X value, which is 0.26, the cumulative probability is 0.6026. For which X value, the cumulative probability will be 0.60. Again, I am going to apply linear approximation, but this time from an inverse perspective. Okay. Now look at the distances. For these two values, the distances to 0.60. The distance of 0.5987 to 0.60 is 13 units, and the distance of 0.6026 to 0.6 is 26 units. So I am going to multiply this value, which is 0.25, with 26, and I'm going to multiply this value with 13, with the opposite distances, and divide the summation to 39, which is going to give me a weighted average of 0.25 and 0.26. So my critical threshold value is 0.2533. Okay. Now you can see this picture to understand this better. So at 0.25, the CDF is equal to 0.5987. At 0.26, the CDF is equal to 0.6026. And I am looking for the X value for which the CDF is equal to 0.6. Now, in order to do that, I need to do what? I need to apply linear approximation in the inverse perspective. So I need to move from here to here. Now you see the proportions of these distances is 26 to 13 units. Therefore, the proportions should be here as well, 13 and 26 units. And this helped me to calculate that the inverse CDF at 0.6 will be 1/3 close to 0.25 and 2/3 close to 0.26, which is 0.2533. Now, another question is this. Again, I am going to identify an X value for which the standard normal random variable is less than or equal to X, is going to be equal to 0.10. So this time, so let me draw you this picture here for part B. The question is asking this. So this is the standard normal distribution, the PDF, the probability density function of the standard normal distribution. And there is a certain X value here, which I do not know yet, X value. And the area on the left-hand side of this X value is 0.10. And the right-hand side will be 0.19. So that is being asked here, okay? So the probability of z being less than or equal to x must be equal to 0.10, and that x is being asked. Okay, so sorry for that. Let me move further. Okay, now check that out. How am I going to identify that x value? Now remember, if you look at my CDF table, I can get the probabilities for positive x values only, okay? If my x is here, according to this figure, if my x is in the negative region, I will not be able to find it. So I am going to use the symmetricity of the standard normal probability density function. And I will say that, let's just check the x value for which the area on the right-hand side is 0.10 and the area on the left-hand side is 0.90. If you find this x value, again, you are going to use the symmetricity and you will call that x value is the negative version of that x value, okay? So this is what this means. If I am going to identify the x value for which the cumulative probability is 0.10, I am going to look for the z value for which the cumulative probability is 0.90, and I am going to take the negative of it, okay? So this means what? If I am interested in the inverse CDF of the standard normal random variable at 10, that is going to be equal to the inverse CDF, negative of the inverse CDF at 1 minus 0.10, okay? So the inverse CDF at 0.90 will be 1.2817, and the negative of it is minus 1.2817, okay? So I need to find 1.2817. So what does that mean? I need to identify the critical x value for which the cumulative distribution function is equal to 0.90, which is the area on the left-hand side, okay? So let's go back to my table. So let's look for 0.90 now. Where is 0.90? It is somewhere between these 2 points, right? So we have 0.8997 and 9015. So it is, then the answer, the critical value is somewhere between 1.28 and 1.29, right? It should be somewhere between 1.28 and 1.29. Now, again, by using the linear approximation idea, I can calculate that value is 1.2817, okay? So I'm not going to explain the linear approximation again and again and again for every example. You are supposed to do that in your exams, okay, in your answers, because you are engineers, my friends, okay? If you are engineers, you need to use the tools of engineers. Linear interpolation here is a tool of an engineer, okay?